Welcome to section 3.2, day 1, logarithmic functions. Today's objective is to evaluate logarithmic functions. All right, relating logarithmic and exponential forms. So look at this, you have b greater than 0, b cannot be 1, and your x has to be greater than 0. We have the logarithmic form and an exponential form. So logarithmic form is log base b of x equals y. So this is only true if and only if b raised to the y power is x. The way I look at these is sort of like it shows on the right. If I have a base of b, what power will give me back x? If I take b and raise it to a power, what will give me x? That's how I look at it. So you have b raised to the y equals x, and that's how I usually solve these. Sort of keeps it straight in my head what I'm doing. You'll notice those pieces on the top where it says b has to be greater than 0. We cannot have a base that's less than 0. So we can't have log raised with a base of -2. Doesn't work. The b can't be 1. And then the other part is because you'd have 1 raised to the y power, which is just 1 raised to any power is just 1, and that's why that does not work. And then x has to be greater than 0. So whenever we do logarithms or natural logarithms, we have to have a positive number for whatever we're taking the log of. X has to be greater than 0. Can't be negative, cannot be 0. Does not work. Exponential functions are one-to-one, have an inverse, and that is what's showing up on top there. And logarithmic functions are the inverse of exponential functions. So we use these to help solve equations later on, these principles of the inverses. Let's see how some of these work. So we have evaluated log base 2 of 16. So one way to look at it, like I said, is to look at what power, so if you take 2 and raise it to a power, what power would that have to be 16? And the way I usually do this, and it does help if you want to, you'd say 2 to what power, and I'm using y, like it did in the last screen, is 16. So 2 raised to what power is 16? Well, the y has to be 4. So if you evaluate this, our answer is 4. And if you wanted to go completely through this, you'd say 2 to the y is the same as 2 to the 4th. And we're going to do this later on. When you have the same base, you can use the exponent. Y has to be 4. So when we evaluate this, we get back 4. We have log base 5 is 1 over 125. Another way to look at this again is 5 raised to what power will give you back 1 over 125. Some of you guys are going to see this right away. Some might not see it right away. And you can do other things to solve it if you need to. So you have 5 with a y. This is the same as 125 to the negative first power. Remember those negative exponents make things move. And this can further be brought into 5 to the y. And 5 cubed is 125. We have 3 times -1. So we have 5y equals 5 to the -3rd. And we evaluate this, we get -3. A couple of different ways. Some of you guys are going to see this just by looking at 5 raised to the y power is 1 over 125. And you'll understand what it is. Some of you might have to do this manipulation that I'm showing on the bottom to help you see what's going on. So now we have log base 3 is 1 over 27. Pretty much the same idea as the last one. 3 raised to what power gives you 1 over 27. If you see it, you can do it right away. Otherwise, do like we did the last slide, which is this is the same as 27 to the negative first power. We want to get the same base. So 3 to the y, we'd have 3 to the 3rd and to the negative first, so 3 to the negative 3rd power. And we get -3 again. We have log base 17 of 17. Again, some of you guys are going to see this right away. 17 raised to what power is 17? Well, the only thing that 17 can be raised to equal 17 is 1. And this is going to lead into some of our properties of logarithms. So the basic properties of logarithms. Again, b has to be greater than 0. B can't be 1. X is some real number. Then the following are true. Log base b of 1 is 0. Doesn't matter what the base is. Anytime they take the log of 1 or natural log of 1, you get 0 back. Log base b of b is 1, just like we showed in that last one. Log base 17 of 17 was 1. Log base b, b to the x, is just x, those inverse properties. And b raised to log base b of x is also x. These are called the inverse properties, those last two. And we're going to use these properties. One thing I forgot to mention earlier, if you just have log and there's no base written, let's just say it 7, we don't have a base written. The base is defaulted as being 10 if it's not written. So we don't write the 10, we don't have to write the 10, but if there's no base written, that means the base is 10 for when you're dealing with a log. So log base 8 of 512. This is sort of like we did earlier. We're looking at what power of 8 will give you 512. This is 512 is 8 to the third power, by the way. Then we get that this evaluates to 3. You could break this down further and take 8 to like 2 cubed, break 512 down to 2 to the 9th, and work it that way also. But hopefully you can see if we have the base of 8. Hopefully we can do some manipulations to see if 8 raised to some power will be 512. There will be some of these later on we'll have to use our calculators for. All right, so we have 22 raised to the log base 22 of 15.2. For this one, we can use our inverse property. And when we do this with our inverse property, we find out that we get 15.2. Base of the 22, log base 22 wipe each other out, leaving just the argument 15.2. And this is using our inverse property. These inverse properties come in very, very handy later. So here's some more basic properties. They link into what we did in the last one where we had the log base b. Now we have log, the base is 10. So log of 1 is 0, the log of 10 is 1. Log of 10 to the x is x, because these all have the base of 10. So 10 log of x is x, using those inverse properties. Again, it's because the base in these cases are all 10s because it's not written. So we have log of 10,000. So again, we can look at 10 raised to some power is 10,000. And when you do this, you should hopefully realize that since we have 4 zeros, 10 raised to the 4th power is 10,000. For b, we have 10 log 12. Well, remember that log 12 is the same as log base 10 of 12. And all we get back is the 12 because it's our inverse property. Then we have the log of 14. This one, there is no way to have a nice answer where 10 to the y equals 14. There is no nice exponent, so you end up using your calculator. And if you ever have one of these, you will be able to use scientific calculators for sure. Some of these you will not. You will run into some of these where we can't use these properties and you have to use a calculator, but we always want to use our properties unless we can't. So log, when you do this on a calculator, is approximately 1.146. And there is a log key on your calculators. Then we have the log of negative 11, and this goes back to what we said earlier, is where you cannot take the log of a negative number or 0. So this has no solution. It's one of those big things. You cannot take the log or natural log of negatives or 0. All right, now we're going to go to logarithm with base e. So logarithm with base e is called the natural logarithm, and it's almost always denoted ln for natural log. And y equals ln of x is the inverse of y equals e to the x. Has the same properties we did in the last two. Ln of 1 is 0, ln of e is 1, ln e to the x is x, e ln of x is x. So the same properties again, except for now we have a base of e. That's the only that's different. We can use these properties again to solve natural log functions. So ln of e to the 4.6, since ln is a base of e, we just get back our exponent, 4.6. This again is using our inverse property. Just letting you know how we're getting these. B, we have the ln of negative 1.2. We cannot take the natural log of a negative number or 0, so this is no solution. Then we have E ln of 4. Again, this is one of our inverse properties. We get back 4 because we're taking E to ln of E 4, so that comes back 4. This is again an inverse property. And then the ln of 7. There is no nice way to do this. So, because you look at this, E to some exponent has to equal 7. There is nothing nice. You end up using your calculator, and you get 1.946. This is how we do natural logs. That is all for section 3.2 day 1. Today we looked at logarithmic forms and how they're related to exponential forms and how they're inverses of each other. Then we looked at the properties of logs, we looked at the property of natural logs, and how we can use these to evaluate expressions. Thank you for watching and have a nice day.